So something else that might be interesting for us to explore is the relationship between gradients of parallel and perpendicular lines. So here we've got a box, and we're going to talk about a few of the lines that relate to this box. One is a line that goes along the bottom. One is the line that goes across the top. Then we've got the line that goes down the right-hand side and the left-hand side of this box. So first, what is the gradient of the bottom side of this shape? Well, gradient, as we know, is just how many steps up did we go for every step, one step we take to the right. So if I take, this is the line that we're talking about. If I take one step to the right from 2 till 3, how many steps up do we take? 0. So our gradient is just 0. Now we might wonder, how is this related to the gradient of the top side? Well, for the top side, for every one step we go across, 1, along this line, we take 0 steps up. So again, the gradient is 0. So we've just found that here and here, they both have the same gradient. It might look a bit obvious. But then, if I were to spin the cube around on this set of axes, and I want to ask, what's the gradient of the bottom side now? Well, we'd have to say, we're starting at this point. This is the bottom. We're going to this point. And from here to here, we have to go down 3 steps. And we have to go across 4 steps. So this is what we might traditionally call the rise. And this is what we would traditionally call the run. So if I just bring this over to somewhere where I can do some drawing. We can see that here, the rise and the run, so rise is -3 and the run is 4. So rise over run equals -3 over 4. And so if we call this the gradient of the bottom side, it's just -3 over 4. How does it relate to the gradient of the top side? Well, let's go back to our picture. Here, we're going from this point to this point. So the rise in this case is from here, down like that, down 1, 2, 3, so that's -3. And our run is from here across to there, so that's 1, 2, 3, 4. So that's +4. If we call this the top, where this is the bottom, then we could say rise over run equals -3, which is our rise. Stepped in the y direction from here down to here, and over our run 4. So it's just -3 on 4. This is the gradient of the top. What do you know? They're the same. So we can conclude that for any two parallel means like train tracks, lines, the gradient will be the same. Good to know. The gradient will be the same. So we've just found that no matter how we rotate this square, you can imagine on this diagram, if we were to rotate it like a little bit anti-clockwise, a bit more, and it were to come out like this, you can see that again, this gradient and this gradient would be the same. So for any two parallel lines, the gradient will be the same. Okay, now, ready for a harder question? What's the gradient of the right-hand side? Maybe pause the video and have a think about it. Well, here we knew we went down 3 steps and across 4. So what would be our best guess of what happens here? Well, it kind of looks like, again, I'll take a bit of a picture here. It kind of looks to me like if I were to we'll just rub out this 3 so it's not distracting us. If we were to take where's my pen? Hiding. If we were to take this triangle -3 and 4 and we were to rotate it to here, maybe something like this. It's not going to work. And we were to rotate it, take that triangle, move it over here, and rotate it. Well, it looks to me like it fits like right there pretty perfectly, doesn't it? So we've just found that when we go down 3 here and across 4 here, that means that this line is associated with going across 3 and up 4. So if we call this line, or the gradient of this line, maybe M1 in this case, and then we call the gradient of this one M2, then we could write here that M2 equals rise over run, which we can just leave as 4/3, and that for this one, M1, our rise is -3 because we're going down 3 steps, and our run is 4. So the question is, how does it relate? Well, we've already answered how the top relates to the bottom. So how does that relate to the gradient of the bottom? So how does this gradient of this side relate to this one on the bottom? Well, we've done 2 things, haven't we? How are they related? But to go between these, we have to 1, change sign. So if we're going from top to bottom, we need to times by -1, or we need to go from positive to negative, and if we're going from the bottom to top, we have to go from negative to positive, positive to negative, depending on which way we're going. And the other thing we have to do is flip rise with run. Great. Now, there might be a tricky thing. So in this case, we've given it as a ratio or as a divisor, but you might be given another question. For example, like we might just have a bit of the coordinate system like this. Might be given to you, and you might be asked something like, graph has gradient m equals 0.5. What is gradient of a line perpendicular to this? Question mark. Interesting. Well, that might seem a bit tricky. First off, what does perpendicular mean? Well, perpendicular means at right angles. So this line is perpendicular to this line, and on our box, you know, this line's perpendicular to this line's perpendicular to this line, perpendicular, perpendicular. So that's what perpendicular means. So first off, what is a gradient of m equals 0.5? Well, it means for every step we go across, we have to go up one step. If we go across another step, we have to go up half a step. Sorry, I misspoke then. For every step we go across, we have to go up half a step. For every step we go across, you have to go up half a step. Another step across, have to go up another half a step. So it's going to look like this. And what would a perpendicular line look like? Well, we know from what we've just done that if this one tells us across one up 0.5, our new formula is going to say across 0.5 down 0.5, which is the same as saying up negative 0.5. So, for example, this could be, say we wanted to start here and draw a line that's perpendicular. Well, we know if we go across half, we have to go down 0.5. And here, or we could look at it the other way. If we go across negative 0.5, we have to go up 0.5. So across negative 0.5, I've just misspoke again. This should be down 1 or up negative 1, shouldn't it? Down 1, up negative 1, or if we go across negative 0.5, we have to go up 1. So we can see that, oh, then I'll delete that point again as well, because that's a bit confusing too, isn't it? So we can see here that we had originally this across 1, up 0.5, and then when we flipped it, we had to change the sign, so we have to change either the sign of this one or this one. So in this case, we change the sign of the second number, and we also have to flip the rise with the run. So instead of 1, we had 0.5 here, and instead of 0.5 here, we had 1 here, and we could do it this way as well. And that's going to produce this line as well. Great. So the final question we had here was, can you come up with a formula that relates the gradient of one line, call it M1, to the gradient of a line that's perpendicular to it? Call it M subscript 2. Well, let's finish off in black. So the formula here is going to be the gradient of line 1 equals negative 1 over M2. So this is because this negative takes the gradient of the first line and swaps it into a negative, and then this 1 divided by is going to take whatever this M2 was, or whatever M1 was, and flip it on its head. So if the gradient here is, we can use this example, if the gradient here, M1, is 0.5, e.g. 0.5, oh, we'll call this M2. M2. M1, finding this one, equals negative 1 over M2, which was just a half. And negative 1, how many halves? Well, in 1, there are 2 halves. So in negative 1, there are negative 2 halves. And we find out, does that make sense for this M1? Well, if we go across 1, we go down 2. Negative 2. So check the rise over the run equals negative 2 over 1. Rise over the run equals negative 2. Fantastic. So that's been a really interesting exploration of the gradients of parallel and perpendicular lines, and we found that for any two parallel lines the gradient will be the same, and for any two perpendicular lines the gradients will be related by this formula. And another way, might be easier of thinking about that, is the sign needs to be changed and we need to flip the rise with the run.